Welcome to the solutions to problem set number 10, where we look at matrix groups. It starts with an easy exercise if you know about determinants. We are looking at the special linear group of degree n over any field f, which is defined as all the non-singular matrices, meaning the matrices with non-vanishing determinant, meaning they have an inverse matrix, such that the determinant is 1. And we're supposed to show that this is a subgroup of GLNF. So and I abbreviate this here with G. So first of all, we have to show that G is not the empty set, but clearly the identity matrix with n ones on the diagonal and zeros elsewhere has clearly determinant 1, so it's an element of G. And now we're using the condensed subgroup criterion. We take two matrices in G and check that then A B inverse also lies in G. And this simply follows from the multiplicativity of the determinant, because this here is the determinant of A times the determinant of B inverse. But this here is the same as the inverse of the determinant of B, the inverse now in the field F. But this is 1 times 1 inverse. So this is 1, meaning that this product AB inverse again is an element of SLNF. So by the condensed subgroup criterion, the claim follows. You should always write that down. I'm a bit lazy here at the blackboard, but you should write down from what I just said, okay? And this is already the proof. All right, next exercise. Also pretty easy if you know about matrices. We take the upper triangular matrices with entries from any field F. Those are the matrices of this form. Here on the main diagonal, I have two entries that are both not 0, because we're in a field, there are no 0 divisors. So if the product AC is not 0, then neither A nor C can be 0. And they, of course, are all from the field F. I'm actually not quite sure if this here with zeros here would also be called an upper triangular matrix. I'm not sure. So maybe this is not correct in terms of linear algebra, but this is our abbreviation for this set. And here we are concerned with showing that this is a subgroup of GL2F. So first of all, as I've just said before, if we take any matrix from here, I abbreviate this by G, then its determinant is A times C, just the entries of the main diagonal, which by assumption is not 0. So this matrix is non-singular, so it is an element of GL2F. So this here, G, is a subset of GL2F, and clearly it is not the empty set, because again, for example, the identity matrix would be by definition an upper triangular matrix. So let's again apply the condensed subgroup criterion. We take two matrices of this set, and we have to show that A times B inverse again is an element of this set. So for this, it is useful to remember the formula for the inverse of a 2 by 2 matrix. It is 1 over the determinant of this matrix, which is D times F, and then you change the entries on the main diagonal and you put a minus sign here. If this is new to you, please convince yourself that this matrix times this here is indeed the identity matrix. Okay, let's do it together. Also for me to check if I remember the formula correctly, we're doing the matrix product. So we take this column, rotate it by 90 degrees and multiply with this row here. So we end up with df plus 0. Then here d times 0, 0 times d is again 0. And then EF minus EF is 0, which is good. And then down here we end up with DF. All right, that looks good. This here is 0, and here I can cancel. And this, by assumption, is not 0, so this is allowed. So we end up with the identity matrix. Okay, the same here, matrix product. So we end up with AF. F0 is again 0. This is good. Minus AE plus BD and CD. Okay, and we see that this here clearly again is of this form. I pull in this factor here, then I obtain field elements, and if I multiply those to check this condition here, I also have this factor twice, so I end up with 1 over df squared times AF times CD. So I can cancel one factor D, one factor F, and I end up with this. This by assumption is not 0, this by assumption is not 0, so the product of these here with this factor is not 0, so this shows that this is of this form here. It's upper triangular with non-vanishing determinant, so AB inverse again is an element of G, thus showing by the condensed subgroup criterion that this here is a subgroup. Again, write this down yourself. Okay, and this, by the way, was completely unnecessary because by assumption A and C is not 0, D and F is not 0, so clearly this expression here is not 0, but whatever. So exercise number 3. That's a very nice example. I wrote as a footnote, I found that on math.stackexchange.com. It's a very good place to look up problems like that, where you can find a lot of hints and answers by experts from all over the world. So we have these two matrices, A and B, which are clearly non-singular. And we first have to find their orders. This is pretty simple. We raise A to the second power. Then using matrix multiplication, we end up with minus the 2 by 2 identity matrix. Do the steps for yourself if you're a beginner. If you know about complex numbers and their representation as 2 by 2 matrices, this is not surprising because this is the matrix corresponding to the imaginary unit I. And I squared is minus 1. So this is the exact analog in the matrix representation of the complex numbers. So a squared is not the identity. What about a to the third power? This is a squared times a. A squared is minus the identity matrix times a. This is minus a again, not the identity matrix. So the order is neither 2 nor 3. But a to the fourth power is minus the identity matrix squared, which of course is the identity matrix. So the order of this matrix is 4. I actually forgot if we wrote ORD for order or simply O, not as in the group case. We should not write this here. This could be misunderstood, for example, for the determinant or whatever. So here I write small o of A. Now B squared is this matrix, clearly not the identity matrix, but already B to the third power, which is B squared times B. Fill in the missing steps yourself, please. Doing matrix multiplication is the identity matrix. So the order of B is 3. Now, if you remember this one exercise from the problem set 7, 8 about permutation groups, there we showed that the order of a product is the least common multiple of the orders, but this is only true if those guys here commute. There we had disjoint cycles, and this here is not true at all, because as you can see for yourself, these matrices do not commute, so this here is not correct. Actually, the following happens. A times B is this matrix here. A times B squared is this matrix here, because here we multiply 1 and 1 with this here, so here we end up with 2. Since we are over the rationals, 2 is not 0. We should only, if we are over a field of characteristic 2, this here would be the identity matrix, which it is not over the rational numbers. And now, what do we suspect? Probably that AB to the nth power is 1, 1, 0, and here an n. And this we are going to prove using mathematical or complete induction. Okay, so our claim is, oh, I forgot the parentheses here, because this would be A times B to the n, only the B raised to the nth power. That's not what I mean. I think it would also be okay if you write down AB to the third power, AB to the fourth power, and then you see there's a 3 here, a 4 here, and so on. But it's a nice possibility to train proofs by induction again, especially because here the calculation itself is not difficult. So maybe this helps you to understand, again, the structure of mathematical induction. We start with a base case, n equals 1. In this case, we just showed here that this is true. We get the matrix 1, 1, 1 and a 0 down below, so check mark. Now for the inductive step, we assume that AB raised to the nth power has this form for some n. We do not say this is true yet, we simply assume we have that. This is called the induction hypothesis or inductive hypothesis, and using this we show that then this here, oh, I'm sorry, of course I need the n plus 1 here, that then this here is also true for the exponent n plus 1. And then by the principle of induction we are done, because we showed it that it is true for n equals 1. Then using this we see that it is true for n equals 2. But if it's true for n equals 2, it's true for n equals 3, again by the inductive step, and so on. This is the principle of induction. Okay, now this is pretty easy. Because this here to the power of n plus 1 is the same as this expression to the power of n times the expression. This is always true by a general power law that holds in any group. And now by the inductive hypothesis, we assume that this here is of the form 1 n 0 1 and multiply with the matrix AB, which is 1 1 0 1. Now matrix product, here we end up with a 1. Down there, 1 times 0 plus 0 times 1 is 0. And now the important entry, 1 times 1 plus 1 times n. So you think that this column hovers above here. So you end up with 1 plus n, which is the same as n plus 1. And down there we have this. So we are done. If you're a beginner and do this for the second or third time, please write down at the end, now by the principle of induction, blah, 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 what I just said, to complete the proof. So, but this clearly means that the order of the product is not finite, because this here never becomes the identity, because we are over the rational numbers, so n is never 0. So I never end up with the identity matrix. So this shows a very, very easy example of two matrices. This matrix is of order 4, the other of order 3, but their product is of infinite order. And clearly, this here is an element of the subgroup generated by AB, because this here consists of all the words containing A and B. And A to the 1 times B to the 1 is a particularly simple word that belongs to this group here. But then all the powers of this guy here are in this set, because it is a subgroup, the subgroup generated by A and B, and all those are different. So we end up with infinitely many matrices in here, So the order of this subgroup here is not 12 or 24 or something that has to do with 3 or 4, but it is infinite. So you have to be very careful if you lose the commutativity to say anything about the relation of the orders of the generators, which are 3 and 4, and the order of the group generated by them. A very nice example, I think. All right, exercise number 4. This contains a very important example of a non-commutative group of order 8, here as a subgroup of the invertible or non-singular 2x2 matrices with complex entries. We are given the following 4 matrices, and the set Q8, Q for quaternion, see below, consists of these elements and their negative matrices. So 8 elements taken together. Now this is a finite subset of a group, and then way back we proved that for finite subsets it suffices to check, it's clearly non-empty, suffices to check that the products lie inside of this set again. No need to check the inverses. So all you would have to do is to take all the elements and calculate their products and check if again you end up with one of those 8 elements. This can easily be done, it's just tedious to write down. But I wanted to remind you here of this special case of the condensed subgroup criterion for finite subsets. All right, now in B, we almost have all the products we need, maybe all. Anyhow, verifying these helps you to write down the group table and convincing yourself that this indeed is true. I'm not going to do this here. Do this at your own leisure if you feel the need to have more exercises in matrix multiplication, but this is simply writing down the matrices, multiplying and verifying that this is true. And this here clearly shows that we have a non-commutative group because ij is not equal to ji. Now one more remark. It is possible to define this quaternion group without reference to any matrices. You could simply say I take 4 symbols, E is my neutral element, and then I, j, and k, satisfying those rules here. And then you can write down the group table and find out, well, this here satisfies the axioms of a group, of a non-commutative group, but it is not possible to see from the group table if the so-defined multiplication is associative. And this is a pain in the ass to verify that the abstract definition of the quaternions, the quaternion group, gives you actually an associative operation. So here we have the great advantage that we're inside of a matrix group, and here we already know that matrix multiplication is associative. So if you know about matrices, this here is a much better way to define the quaternion group. All right, so here, check mark, you can do this on your own if you want to. Now we have to find the inverses and the order of the elements. Using this is pretty easy. I to the second power is clearly not the identity, but minus the identity. I to the third power is minus I, which again is not the identity. But I to the fourth power is minus e squared, which is the identity. So the order of I is 4. And the inverse of I is I to the third power, because this here is I to the third power times I, and this is the identity. But I to the third power is nothing but minus I, as we've seen here, so the inverse of I is its negative. And of course, exactly the same is true for j and k, because they satisfy the same relation here. So the order of j as well as the order of k are also 4. And the same is true for the negatives. You can check this if you want. So if I is of order 4, then minus I also is of order 4. So this is very interesting. All the elements of Q8, except for, of course, E and minus E. E has order 1 trivially, minus E has order 2, because its square is the identity. All the other elements are of order 4. And later we're going to see that because of that, this cannot be the same group as di4, the dihedral group of the square, which is also a non-commutative group of order 8. Because they are not all the elements besides plus minus the identity are of order 4. Okay, to conclude, an outlook. Still surprised that this seems to be the right word. It sounds wrong to me, but I hope you get what I'm trying to say. If we write down a linear combination with real numbers a, b, c, d, I didn't put that down here, a, b, c, d, real numbers, and then you take this linear combination of these matrices, you end up with this matrix. And this here is of the form complex number w and its complex conjugate w bar. And here we have a complex number z, and down here we have the complex conjugate, but with a minus sign, because the conjugate would be c minus di. And this here is an element in matrix notation of the famous and notorious Hamilton's quaternions H. To honor Hamilton, they are called H. This is a real four-dimensional vector space to begin with, but it's also a so-called algebra because you can multiply the matrices. Here we have the matrix representation of the quaternions, but it is even more. It's a so-called division algebra, meaning that all the non-zero elements of H have an inverse, which is easy to verify if you use these matrices. And forgetting about the linear vector space structure, this is a so-called skew field. It satisfies all the axioms of a field except for commutativity of multiplication, because those matrices in general do not commute. And if you have more methods of algebra, you can show it's actually not possible to find a field that contains the complex numbers. This here contains a copy of the complex numbers, so this would be a field extension of the complex numbers, which is not possible, as we will see later on. So just some fun facts for the interested viewer. Okay, last exercise of this hopefully enjoyable and not too long problem set. I'm quite surprised myself that I managed to come up with a problem set that is not too long and too tedious. So, and if you've never heard about finite fields, it's okay to skip this exercise. First of all, we take all the 2 by 2 matrices with entries from the field with 2 elements. That, when you hear it for the first time, sounds paradoxical. There can be a field with 2 elements. Well, yes. You simply take z modulo 2z, as we already know from the group example, consisting of these 2 residue classes, 0 and 1, and then you can add them and multiply them, just as we did with addition, and this satisfies all the requirements for a field. So this is a field with 2 elements. Now, how many matrices are there with entries from this field? Well, 2 times 2 times 2 times 2, so 2 to the 4th power, making 16 different matrices, but not all of them have non-vanishing determinant. So you simply by trying out, you find these matrices here. Those are the only ones, namely 6 of them, that have non-vanishing determinant. The others, write them down, all 16, and find out that their determinant vanishes. And for example, if there's a 0 column, 0, 0, then it's already out, because then its determinant is 0. And the order of these matrices are, this here is the identity matrix, so this is of order 1. These matrices have order 2, and these 2 have order 3. So let's do an example. We take this matrix here and square it, so we multiply it by itself. So matrix multiplication, 1 bar, 0 bar, multiplied with that. 1 bar times 1 bar is 1 times 1 bar, which is the same as 1 bar. So the residue class of 1 plus 0 times 1 is the residue class of 0. This is the neutral element, so this vanishes. Then down here, 1 times 0, 0 times 1 gives me the residue class of 0, so the identity. Now for the second column, I multiply 1 times 1 plus 1 times 1, which is 1 plus 1 bar, so 2 bar. But now we are taking the elements modulo 2. So this is the same as the residue class of 0. That's where the so-called characteristic of this field comes in. And the last one gives me this. So this is clearly the identity matrix, showing that the order of this element here is 2. So if you need a little more practice with matrix multiplication and dealing with finite fields, please verify, for example, that the order of this matrix here is 3. Okay, last part of the last exercise, a little bit of combinatorics combined with effect from linear algebra. Let's do it for general P. So we take the 2 by 2 matrices over Fp and want to find out how many of them are invertible. Of course, even for p equals 3, you would have to check 81 matrices. You don't want to do that. And for general p, it's not possible to write down all the matrices and check the determinants. So we use the following effects. The determinant of such a 2 by 2 matrix is 0 if and only if one of the columns is a multiple of the other. So we start with the first column. Everything is allowed here except for the 0 column, because if we have 0, 0 here, then this is clearly a multiple of any second column, because 0 times the second column gives me the first column. Okay? So here we have p times p, making p squared entries that are possible, but we have to subtract 1 for the 0 column. This is not allowed. So here we have p squared minus 1 possible yellow first columns. Now for the determinant not to be 0, this here is not allowed to be a multiple of this. And this of course goes the other way around, because if this is a multiple of this, then by multiplying with the factor, with the inverse of the factor, I also get that this one here is a multiple of that. Or did I? That this one is a multiple of that. So no need to check both. For being multiples, it's enough to check that this here is not a multiple of the yellow one. So to begin with, we have p squared possible columns, because here I can put down p entries and here making p squared possible second columns. But then we have to subtract all the multiples of the yellow column here. How many multiples are there? Well, Fp has p elements, so we have to subtract p, all the multiples of the yellow column. And now we can be sure that the determinant of these matrices with this number here is not 0. Okay, and this just showed that we have p squared minus 1 times p squared minus p possible choices for non-singular matrices, 2 by 2 matrices over Fp. So this here is the general result. If you didn't completely understand that, don't feel too bad. We're almost never going to need GLFP or finite fields in the course of part 1 of group theory. So this was just a nice exercise if you know about matrices and finite fields. So let's check. If p is equal to 2, we should end up with 6 possible matrices here, and indeed this here is 4 minus 1, 3, this here is 4 minus 2, 2, 3 times 2 is 6. For the next prime 3, we already would have 48 non-singular matrices. So GL2F3 is an example of a non-commutative group with 48 elements, and so on. All right, that's it. As always, if you found this video helpful and enjoyed the exercises, let me know in the comments, give a like, subscribe, and I will see you in next week's lesson. Bye bye.